Throughout this series, I've been using the exact radius value of 6371 kilometers for the Earth, which GeoGebra converts so that we can work in miles, feet and inches. But when I'm taking refraction into account, you'll have noticed that I switched to a slightly larger radius for the Earth. Before I explain why I'm doing that, let's listen to a short clip from Flat Earther Brian's logic first.
Well, how are you doing? In my last video, I calculated the amount of over 6R, which is the globe's mathematical version of refraction. It's not real refraction, it's just a mathematical change in an arc length. That's all it is, because their globe, it never has less than a radius of 4618 miles, which means that it's always more than 3959 miles, which is their claimed geometric radius, which is not geometric because it's not measured. It's nonsense. But they have to claim that their globe is a constant arc length of differing degrees of curvature.
That was Brian's logic, trying to understand the what, but maybe not so much the why. So here I have two methods side by side in a GeoGebra split screen. In this method, the Earth's radius is fixed and the light ray is curving. And in this one, the ray is straight, but like Brian says, the Earth's radius gets increased. So without going into the maths, let's see if we can visualize why these two different approaches give us the same results. Blackpool Tower is just over 12 miles away from the camera, and the mountain behind it is just over 50. And from part 8, we already know what to look for. With standard refraction, the ray from the camera to the peak of the mountain should intersect the tower about 32 feet below the observation deck. And even though these are two completely different geometries, they're giving us exactly the same result of 31.6 feet. To see why these are equivalent, we need to think about relative curvature. In order to make this light ray straight, all of its curvature has to be removed. But to keep the gap between the light and the ground identical, whatever we remove from the light ray must also be subtracted from the Earth. We end up with a straight light ray and a slightly modified Earth radius, which we can now use in our calculations that include refraction. The values may have changed, but the relationship remains the same. Back to the split screen then. Here I'm getting GeoGebra to measure the gap between the horizon ray and the surface, for both methods at the same time, for any distance I care to choose. And you'll notice the same hidden height is returned. This is also true for the distance between the surface and the ray to the top of the mountain. Both geometries, independently measured, giving us the same result. So it doesn't really matter which geometry you pick to make your calculations, but you make the maths much easier if you're just dealing with straight lines. And as I said in part 5, they're equivalent. So hopefully this puts an end to the 3000 over 6R videos that we get from Brian. GeoGebra links are in the description. Please share and do hit that thumbs up for me if you can. From me and from Bri.
Thanks for watching.
Catch you later.